Hello? Oh, there we go. Hello, everybody. Thank you for coming. Welcome to Deep Talks Nobel Day. I'm so glad all of you are here. My name is Erin Woodward. I am a communications specialist with Sanford Underground Research Facility. And I'd like to get started by thanking the amazing sponsors who make Deep Talks possible every month. We're sponsored by Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, Edward Jones, and Chuck and Jolene Lichten-Wallner. So can you guys give them a round of applause, please? So this is a very special edition of Deep Talks. If you don't know, we host these events every month, October through May. But this is a very special one. It's going to include a presentation of the 2022 Coors Award, and then a presentation by our featured speaker, Dr. Neta Bahcall, and then that will be followed by a Q&A session. So I'm going to start with the Coors Award. So this is something we've been giving away for a few years now, and every year on Nobel Day, we give the Coors Award to an individual, group, business, or organization that supports communication and outreach experiences in science within the Black Hills region. Recipients demonstrate ongoing support for public outreach in a way that demonstrates a passion for science and a visible commitment to outreach. This year, SURF will recognize the monumental contributions of physicist and educator Peggy Norris with the 2022 Coors Award. As the Deputy Director for SURF's Education and Outreach team, Norris helped build the team into a keystone for science educators in South Dakota. In addition to creating curriculum units, delivering in-school presentations, hosting field trips, and planning professional development for educators, Norris worked to advance the SURF internship program and reach groups that are typically underrepresented in STEM fields. And after 14 years with the team, SURF retired from SURF E&O earlier this year. In retirement, she continues to be a staunch advocate for STEM education for curious minds of all ages. Norris uses phenomena from the natural world to get audiences excited about science, and her personal favorite phenomenon is a solar eclipse. Norris has given presentations about eclipses to public audiences around the state and region. And in 2017, she led a group of students and space enthusiasts to watch a total solar eclipse in Nebraska with NASA's nationwide eclipse ballooning project. And at SURF's citywide science festival, Neutrino Day, she helps attendees peer safely at the sun through a solar telescope. In 2020, Norris planned a trip to Antarctica. That trip would have completed her mission to witness an eclipse on every continent. Due to the pandemic, though, the trip was rescheduled for this December. So unfortunately, she can't be with us today as she is currently on a cruise ship in the middle of the Antarctic Ocean. We look forward to presenting this award to Peggy at our next all-hands meeting, and for tonight, we are pleased to have Peggy's daughter, Molly Brown, with us to read remarks on Peggy's behalf. So please welcome Molly Brown.
Good evening, everyone. For those of you who don't know me, my name's Molly Brown, and I am the EVP of Corporate Strategy at GenPro Energy Solutions. I am also my mother's daughter. So I am going to read some remarks that she wrote while she was on her trip, and then I'm going to talk about her a little bit, because she's not here to stop me. So from my mother, Peggy Norris, good evening. I am honored to receive the 2022 Coors Award from Sanford Lab. Thank you to my daughter, Molly Brown, for offering to step in and represent me tonight, and to the communications and education and outreach teams at SURF for the great work they could do every day. I wish I could be there tonight, either in person or by Zoom, but I am off to a great adventure to visit our most remote continent, the Antarctic. The internet out here in the middle of nowhere is better than I expected, but definitely not Zoom quality. I am never happier than when I am sharing my passion for science with others. It is special to be recognized for only doing what I love. Again, thank you to everyone at SURF who makes outreach a priority, and to my lead Deadwood community for providing a loyal and dedicated audience for our local activities. So that is from my mom. For those of you who know my mom, you know my mom. For those of you who don't, she is a force of nature. Every time I meet someone new who soon discovers that I am her daughter, all I get is, "Your mom is the most amazing person in the world. She's such a neat lady. You must be so lucky to be her daughter." And I am. It's not always easy. It's also not always easy to be my mother. So when I was born, my mother was in her PhD program in Columbia. She was the only woman in her class, and now she had a newborn baby. So what was she gonna do? She didn't put me in daycare. She took me with her. I remember growing up at the Berkeley labs in the Bevatron, the Bevilac, the cyclotron, hanging out in the caves, watching Star Wars in the control room, running down the hallways like when I was 10 years old, nobody stopping me. Oh, that's just Molly, you know, she's here. And having my first college internship where I learned how to build a website in her office. So there was years and years and years that I spent hanging out with my mother in her scientific endeavors. But I was not a scientist. I was a dancer. I was an artist. And I always thought there was somewhat of a disappointment, you know, that I didn't share her love for science. But as years went on and years went on, and Mom decided to retire and apply for the job out here in South Dakota, she was kind of nervous about it because she was a scientist. She wasn't an educator. And she thought that by not having that really long history of being an educator, she might not get the job. Well, she did end up getting the job. So she moved out here. Shortly afterwards, the market crashed in California. I was like, well, what the heck am I gonna do? I'm gonna go visit Mom. So I packed up my stuff and went on the road and ended up at Mom's house in South Dakota. The first thing she did was put me to work. So 4th of July, she decided that we're gonna do a float in the 4th of July parade. And so we made a mock-up model of the Yates shaft out of plywood and nails. And it was so windy that day that I remember it just like halfway blowing out of the truck. She also made me dress up as Grubby the Miner and do cartwheels down Deadwood Main Street in the miner's outfit. So put me to work right away. But I was happy to be part of the community and volunteer at things like Neutrino Day. So soon afterwards, I found my job at GenPro, which is definitely a STEM job. I work with engineers, scientists. I'm an economist, so math is in it every day. And as soon as I got that job, she's like, "You need to come to this event at the Girls Club and like talk about what you do with all these girls, or you need to come to Women in Science with me." So slowly and slowly, I kind of kept getting like talked into doing these things with my mom as we're spreading the word about science. And it was so neat to watch her interact with all of these different people. And I attended some of her Train the Teacher sessions and a lot of her Women in STEM sessions from ages from this through the Bahcall scholarship students. We would take them on Pactola and go on like the pontoon boat rides. And so it's been really, really amazing to watch my mom blossom from a place where she was kind of stepping out of her element as a pure scientist and into this new role as someone who is completely in the public eye. And to say that I am proud of my mother is an understatement. To say that I hope to live up to her footsteps is an understatement. And I only hope that I can continue and help through my own development and career development and personal industry and personal path to be able to continue her work. So congratulations to my mom. She's awesome. I wish she could be here.
Thank you so much. Awesome. That was amazing, Molly. Thank you so much. All right, and now it's my pleasure to introduce tonight's speaker, Dr. Neta Bahcall. Neta Bahcall is a member of the National Academy of Sciences and has been a lecturer for numerous organizations, including the Nobel Symposium in Stockholm. Her research has focused on dark matter, the structure of the universe, quasars, and the formation of galaxies. Neta Bahcall continues to do research and teach at Princeton University. And for decades, she worked alongside her late husband, theoretical physicist John Bahcall. Together, they wrote more than 30 scientific papers. And tonight, Neta will explore John Bahcall's contributions to fundamental physics research and his work in neutrino astrophysics, which influenced countless experiments and projects for more than 4 decades, including the solar neutrino experiment at Homestake. Please help me welcome Dr. Neta Bahcall.
down at the SERF lab, seeing some of the amazing experiments that are being done here today. So I want to, first of all, congratulate everybody at SERF, the physicists, the scientists, the engineers, the technicians, everybody that works at SERF on the amazing achievements that are happening at the lab. And what I want to share with you today, and I'm happy to sort of give and take, I want to share the stories of one of the most, probably the most amazing experiment that was done at the Sanford lab, started 60 years ago. That's the search for solar neutrinos. And that's an example of an exemplary science project that ended up with solving a big mystery. And some of the current experiments will hopefully help solve some similar big mysteries that we have about our universe. So I want to share some of those stories with you today. And if you have any questions as we go along, feel free to ask and interrupt, and we can discuss it. So, so I'm going to talk about John Bahcall, my husband, and Ray Davis, the famous scientist who created the solar neutrino lab here, the first big experiment in the Sanford lab. It was not called Sanford lab, but the underground lab here. And here is a picture, and we'll see this picture a couple of times. It's one of the iconic pictures of Ray Davis. I don't know if we have pointer, but Ray Davis is the one right by the tank in the lab, and this is John, and that's going back almost 60 years ago. So Bahcall and Davis, it's a story, it's an amazing story of science discovery, and I want you to see how science sometimes works. Of vision, two visionaries that really looked for the future with vision and precision, of courage, because they both stood, as I'll show you, against a lot of negative comments over many years. Persistence, they persisted, and sometimes you have to really persist, not give up. Persisted in science, and they did it together for over 40 years until the big final discovery that was totally unexpected. They started with the simple, basic question, how does the sun shine? Sounds very simple. We see the sun. It's our sun. It warms our earth. We are here because we are warmed by the sun. We can have life here on earth. How does it shine? What produces all this huge amount of energy from the sun? That basic question, seems very simple question, was for a long time, 150 years, was very controversial. Nobody knew even how to address it. Originally, they thought just gravitational energy pulled the sun closer together and generated energy. That was incorrect. Until famous physicist Hans Bethe in the 1930s suggested that nuclear reactions, nuclear fusion reactions at the center of the sun, where the sun is very hot, produce this amount of energy, just like hydrogen bomb, produces a lot of energy, and that's what hits up the sun. So that was the idea, the scenario, the theory, that the sun shines by nuclear reactions. But nobody could test that. It was not tested observationally. So we don't know, you can have theories about anything, you don't know if it's true or not until you observe it or test it experimentally. So that's the story, that's how they started. So Bahcall and Davis decided, again, almost 60 years ago, to test if the sun shines by nuclear reactions in the hot core. It was never tested before, and as you will see, it is very difficult to test the core of the sun because we cannot see the core of the sun. When we look at the sun, we only see the surface of the sun. We cannot see what's happening inside. It's way, way deep in the sun. We don't know what's happening. So what happened, and I'll show it in more detail, this is just like a highlight. So what the way they work is that John Bahcall developed an accurate model of the sun, all the way from the exterior, all the way to the interior. We'll talk about it briefly. From that, he calculated the fusion reactions in the core of the sun based on the temperature and density and what's happening in the sun. Again, you cannot see that. So think about it. You develop all this theory and you cannot really see that. And if those nuclear reactions happen indeed in the core of the sun, they emit neutrinos, and we'll talk what neutrinos are briefly. The only thing that can escape from the core of the sun quickly from the sun to us in a few minutes are neutrinos. So these are the only messenger from the center of the sun that can reach us, and we can try to detect them. So John did all the calculation of the solar neutrino of the sun, then how many neutrinos, those are called solar neutrinos, neutrinos coming from the sun, calculated how much would an experiment be able to detect them. Ray Davis then built the experiment right here in the lab, and that was the initial stages, and both John and Ray worked together as colleagues, pioneers. They pioneered the whole field. John on the theoretical side, Davis on the experimental side, led the field, and they were close friends for 40 years until the end. So let's go a little bit more detail. So the sun is just, as you all know, it's just a ball of very, very hot gas, mostly hydrogen, some helium, some other gases. The temperature on the outside of the sun, in the surface, is close to 6,000 degrees, very hot on the outside. By doing, not simple, by doing the physics model of what a hot ball of gas like this does over the temperature of equilibrium, because we know the sun is not exploding, it's not collapsing, it's in approximate equilibrium. John calculated the full model of the sun, and getting in all the way from the surface into the center. At the center, the temperature is about 15 million degrees. So it's very hot. That's hot enough for nuclear fusion reactions to happen, and those generate the neutrinos. So how does the sun shine? And by the way, when we say how does the sun shine, it's not only the sun. If we figure out how the sun shines, all the stars, or most of the stars, are just like the sun. So most of the stars will shine by nuclear reactions in their cores. So it's not just to figure out about one star, the sun, but it tells you, it tests whether all stars shine by nuclear reactions in their core. So it was a very ambitious goal. Again, we talked about you cannot see all the way into the interior of the sun. The only particles will escape are these neutrinos that were believed to be massless. Now we know that they have a little bit of mass, but they don't interact much with matter, and that's why they can escape quickly. They fly with the speed of light. They come to the Earth. They don't interact very much with almost anything, but a few of them could hit a detector underground, shielded from background, and then if you know how to do that, you can extract the product of what the neutrinos interact with, and that's what Ray Davis eventually did. So John calculated it all, calculated how many neutrinos the sun produces, calculated if Ray Davis builds an experiment of that many tons, of that size, with chlorine, how many neutrinos will hit some chlorine atoms in it. They'll change it to argon. Then Davis will extract the argon from the tank down in the mine, take it back to Brookhaven, count how many atoms of argon, a few, just a handful every few months. A very difficult experiment. Count how many, and that will tell you whether the sun that John calculated shines by nuclear reactions or not. So that's the basic story. The nuclear reactions that happen in the sun are the hydrogen. It's called the hydrogen cycle, the burning cycle. It's fusion. I'm not going to go to the detail, but it's a set of nuclear reactions, the end of which is 4 protons, the nucleus of the hydrogen. 4 protons at the end create a helium particle, 2 positrons, and 2 neutrinos. So that's the sum of the nuclear reactions at the center of the sun. The other particles you cannot see, they cannot escape out of the sun, nothing else escapes from the center, only these little neutrinos that barely interact with anything is what John calculated, their energies, their number, and how many of these can chlorine in a detector detect, and therefore how many neutrinos will be produced and detected. By the way, neutrinos are just the most abundant particle in the universe. If you, as John used to always say, if you put your thumb, every second you'll have about 100 billion neutrinos hitting your thumb. Put your thumb, that's what you have. You have so many neutrinos hitting you all the time, and we don't know. They don't interact with anything. So we don't even know that exists. So can you imagine in a big tank, they can only hit a few particles of chlorine and change to argon for Ray Davis to detect. So you can see how difficult it is, and I'll say a few more words about that, both on the theoretical side and on the experimental side. And those two were married together all along. It was not one without the other. The chlorine experiment could not have been done without the theoretical model, because you don't know what you expect. You don't know if you can even detect anything. So these are the early days. John started as a postdoc at Caltech, and that was, of course, in the mine roughly at that time. And he was an expert, got his PhD in weak interaction. Those are the nuclear reaction that produce neutrinos, beta decay, radioactive decays. And that's when he began the collaboration with Ray Davis. The motivation, as John said, to see deep into the interior of a star and thus verify directly the hypothesis of nuclear energy generation in stars. So not just in the sun, they tested on the sun, but it will apply to most stars. As I said, he developed the solar model and the rate, and it was a monumental project, and he kept improving it for decades to come. You have to calculate what, under the physics condition for the gas, what is a temperature profile from the outside, where we can see that it's about 6,000 degrees, all the way to the inside where it's 15 million degrees. And the temperature on the inside he had to calculate to better than maybe 1 or 2 or 3%. Can you imagine that? Because if it was off by 3%, the number of neutrinos would change by a factor of 3 or 5. It was very sensitive to the temperature. So the temperature profile, the density profile, the composition, how much hydrogen, helium, other elements, and that changes throughout the sun. All of that had to be calculated. The nuclear reaction rates all had to be put in order to know how many neutrinos are produced. And the energy spectra are determined. Have to use the propagation of neutrino, and many, many other solar physics input had to go in there. So that was a monumental project to do. At the same time, and he derived how many neutrinos will be from the sun, from this reaction, will be captured in Davis experiment, and the original number showed that Davis experiment will never detect anything. It was too low, but then he realized that there was some what's called super allowed transition of a neutrino on a chlorine particle, chlorine atom, that increased it by a factor of 20, and that is what enabled Ray Davis experiment to start, to be funded, only because of John's calculation, Ray Davis experiment. Both Ray Davis and John went to, and I don't remember which agencies, whether it was DOE or NSF, but it got funded. First, it has to go through Brookhaven, where Davis was. It got funded because John saw that it can be, he can detect something. Before that, it looked like he won't be able to detect anything. So that's what enabled the experiment. Again, so that's, I told you, you'll see it a few times. That's when it started. So that's how it all started. This is a similar picture. That's John, again, roughly at that time when it was started or in the beginning. And I'm showing it because this is also a personal time. This is approximately when I met John. I was in '65 when I met John. I was a graduate student in physics, in nuclear physics, at the Weizmann Institute in Israel, and John came for a visit. He was a junior faculty at Caltech already at that time. That's how we met. We fell in love, we got married, and then I moved to Caltech and finished my studies there. So, so it's a personal story for me, and I remember that when we met at the Weizmann Institute, he gave a talk, and I was sitting like that in the talk, and that's how we met. We talked after that. And I remember that when we started going out then in Israel, he was there just for a week or two, he told me with great excitement about this amazing project he's doing about trying to detect solar neutrinos and how the sun shines. And he was so excited about it that it was just amazing. He just loved the topic. And he kept that love for solar neutrinos for the entire 40 years. And that's when it started. So from that personal story, I'll show you John and myself at that time. And that was, every time I saw this picture, people go, ah. Anyway, that's when we were young. So that was in around '65. That was just before we were married. And I'll show you later pictures of us 40 years later, too. So that's why I remember it so well, and it's personal to me because I know that's when he worked on it. He was very excited. Nobody knew what the results will be, but he was enormously excited about his work. So what is a story? So Bahcall and Davis then proposed, when John saw it can be done, they proposed a chlorine experiment to test how the sun shines in the way that I described. John calculated how many and what to expect. Without it, you don't know how to compare with anything. And Ray Davis built the chlorine experiment that was up in the lab for many years, starting in the '60s. Now it's occupied with the new experiment, with the LZ experiment that we visited today, and that was a very inspirational and moving visit today for me. So he built the chlorine experiment. Again, neutrinos on chlorine produce argon. He got the argon counted, and then he knows how many neutrinos, what energy, and the rate, and so on, in order to compare with John's experiment. The first results came in very quickly. It didn't take 40 years to get results. The first results came in '68, so it only took about 4 years to get some results. He detected only a few neutrinos per month, so in a few years you detect enough to see. So the first result came in very quickly in '68, and the bottom line of this detection was good and bad. The good was he detected solar neutrinos. John said he will detect them, he detected them. But the bad news was, so that was a big success. Already tells you how the sun shines, because he detected the neutrinos expected from the nuclear reaction, so it happens. The bad news was that the number that he found was 3 times less than what John predicted. And nobody knew why. So he found it 3 times less. And everybody, as I'll show you later, started saying, well, it's a factor of 3, maybe Ray Davis can get all the neutrinos out. Maybe he misses a few. Maybe John can't calculate. How can you calculate the center of the sun temperature so well? We cannot see it. We don't know what's happening there. Top physicists kept saying it for a long time. And I'll show you their statements because it tells you about how science is done, which I think is really important. So the factor of 3 became what was known for the next 35 years as the solar neutrino problem. You detect neutrinos from the sun, so we know how stars shine. But it's less than what's predicted. It's a solar neutrino problem, or some people call it the mystery of the missing neutrino. Where did the missing neutrino go? There is a happy ending to the story, to that mystery, which we'll come to. But I want to tell you how it went. So here is a curve that you can visualize. This is the predicted solar neutrinos, and the dots there is what John and his colleagues predicted all the way from 1968 all the way to over 2000. It didn't change very much. John kept improving the models. Every time somebody complained, maybe there is mixing in the sun, maybe there is this in the sun or that in the sun. He calculated, he showed, he checked it all carefully, and he showed none of that other claims worked. Was consistent for 40 years. He got the same prediction. Ray Davis' experiment is in the band here. The observation were, again, consistent, plus and minus, up and down, but they were consistent over 40 years, or as long as the experiment went. That's a difference of a factor of 3. That's a solar neutrino problem. Why do we see only 1/3 of the neutrinos? What happened to the other 2/3? Is the sun model wrong? Is Ray Davis' experiment wrong? What's going on? That was a solar neutrino problem. So there were 3 possible explanations to the mystery of the solar neutrino. The first one, as we just said, the Ray Davis experiment is wrong. How can he possibly find all these few neutrinos in this huge tank? Well, maybe he misses a few. It's not a big deal. He missed a factor of 3. That was, many people claimed that. And that's one reason why it lasted like 35 years until we got solution, because many physicists, top physicists, Nobel-Prize physicists, claimed that, well, it's only a factor of 3. Maybe he didn't count everything. They were wrong, as you'll see. Second is maybe the astronomy wrong. How can John possibly calculate the center of the sun that we cannot see anything so well? Well, they claim that, and that's what took 35 years from John to keep improving and improving and improving the model. They were all wrong. And the third possibility that was very unlikely, that very few people thought about, almost nobody thought about at that time, is that the physics is wrong, that Ray Davis was right and John was right on the astronomy side, but that the physics is wrong, that the physics of neutrino, that all physicists, standard model of physics told us that neutrinos have no mass, they're single particles, and we'll come to that, maybe that is wrong. And we will see in a moment that finally, unexpectedly, that is what happened. So Ray Davis was right, John was right, physics was wrong. And that is what a big discovery means. So they didn't look to discover that physics was wrong. They started looking to see, how does the sun shine? Just catch these neutrinos and know how the sun shines. They found how the sun shines, but they also discovered something really, really important, that physics had to be changed, standard model of physics. So as I said, many ignored it, but John and Ray, they never questioned it, never. I remember sometime asking John, well, do you think some of these claims, could they have something in it? He said, no, I checked it all. That cannot be. He did various scientific checks and cannot be. And he and Ray looked at the experiments and suggested, let's try, put a neutrino beam where you know how many neutrinos are there and see how many you get out. And he got out all of them. So they did the checks like real top scientists. You check everything along the way. So they did it for 35 years. They persisted, not because they were stubborn. Sometimes you can be wrong and stubborn. Not because they were stubborn, but because they tested themselves and each other all along, and they answered any possible complaint or possible error. They checked and checked, and they were convinced that everything they did was exactly right. And that's why they persisted. And they persisted, and again, like I said, they were right. And the reason that it took 35 years is because many people doubted the experiment, they doubted the astronomy, and they really didn't think it was worth putting much more effort into it. But John and Ray did. Ray kept the experiments. John kept suggesting new experiments to test that. So for the next 35 years, it was, like I said, extensively investigated, both theoretically by John, experimentally, and then both John and Davis suggested various other experiments, including the Kamiokanda in Japan, SAGE in Russia, Galax in Germany, and of course at the end, SNOW in Canada. In order to understand why there are only a third of the neutrinos. Those other experiments was not a repeat of Davis' experiments. They were all designed very carefully by John and Ray to test different parts of the nuclear reaction rates, different reactions. So it's testing different parts of the center of the sun reaction rate. So it's not repeating Davis experiments directly. All those experiments show discrepancies with the Bahcall solar model that became known as the standard solar model. Eventually, in the 1990s, there are new measurements that were not neutrino, but they were helioseismology, measuring the seismology of the sun, how the sun shakes seismologically, came out. And the helioseismology measurements were very accurate, and they tell you what happens at the core of the sun. They reflect the temperature and the conditions at the center of the sun. And when those, when those results came out, excuse me, when those results came out, John was elated because those measurements of the helioseismology matched perfectly with John's calculations of the center of the sun, of the temperature, of the density, of the environment at the center of the sun. So it was then impossible for others to say the astronomy was wrong, the center of the sun, you cannot calculate it. The helioseismology matched it perfectly well. So that was a very important, exciting time for John and for solar neutrinos. And then even in 1990, Bahcall and this famous physicist Hans Bethe, who first suggested nuclear reactions, suggested that combining the data from the different experiments, because they all differed in different ways. So it was clear that it cannot be that the astronomy was wrong. It was clear that it cannot be that Davis experiment is wrong, because other experiments get different results than the solar model too, but different than Davis result. So it became clear then when John and Hans Bethe put it together, it cannot be, it only can fit when you have new physics for neutrino. Unexpected new physics for neutrino. And that showed that the astronomy, as I said, and Bahcall, the theory was correct, the experiment, Davis, and the others were all correct, and that new physics was needed. Again, that's putting all the experiments together. And I'll show you here just one graph that I know John loved to show, and I'm not going into detail, but it just shows you, I'll just briefly tell you, each panel is a different experiment. That's Davis chlorine, this is Kamiokanda, the Japanese, that's a gallium experiment, and this is a snow experiment. The big band in each one, the tall band, is John's prediction of how many neutrinos expected in some units. Doesn't matter what the units are. This is how many neutrinos expected, and next to it, in the blue here, is how many Ray Davis found. You see? Only a third of it. This is what Kamiokanda found, the Japanese, doing it two different ways. Also, not the same as what John predicted, half of that. But not the same fraction as what Davis did. This is gallium experiment. Forget about the different colors there, but this is all from the John theory. Again, much less than what John predicted, but if you look at the red, this is for the main proton-proton chain. It agrees with John's prediction there. And finally, the snow experiment, when they looked at only type of neutrinos that Ray Davis was looking at, they also find something very much the same as what Ray Davis compared to John, 1/3. But when they looked, and I'll come to that in the next slide, at all the neutrinos that come from the sun, not just one type, which is electron, it was expected there will be only one type called electron neutrinos that come from the sun. That was physics. That's what physics predicted. Just one type of neutrino, electron neutrino, comes from the sun. That's what Davis did. But John calculated all these neutrinos because they were supposed to be the same. When Snow looked at all the neutrinos, they got exactly what John predicted. And that is the physics of physics of neutrino was simply wrong. All the physics of neutrinos and the physics book had to change, standard model of neutrinos. So again, so what is the solution? And that came finally from the Snow experiment in 2001. We know that there are three types of neutrinos. There are electron neutrinos, muon neutrinos, and tau neutrinos. Standard model of physics believed all along, check all the textbooks up to that time, these are three different types of neutrinos. None of them have any mass. The sun produces only electron neutrinos. Those are the nuclear reactions that produce only electron neutrinos. And that's what John calculated, how many neutrinos come from the sun. Davis detector, by getting the neutrino on chlorine, that reaction is just for electron neutrinos. So if the sun produces just electron neutrinos, but the electron neutrinos change their type to the other type of neutrinos, it's a quantum effect, quantum fluctuation effect. If they change from electron to muon or tau neutrinos, it's called solar oscillation. They change their personality. It's a personality disorder. They move from electron neutrino to muon neutrino to tau neutrino and then back. If they change on the way from the time they emitted all as electron neutrinos at the center of the sun, but if by the time they reach Davis experiment, 2/3 of them change to something else, Ray will detect only 1/3 because his experiment was only to detect electron neutrinos. And that's what happened. So nobody expected that to be the case. That was not part of the physics textbooks. Neutrinos were not supposed to do that. And the only way the neutrino can oscillate is they have to have mass. And neutrino will always say neutrinos are massless. Now we know neutrinos are not massless. They do have mass, and that's still a challenge for the standard model of physics to know why neutrinos have mass. So they discovered something very important in physics. So the Snow experiment, so the neutrino oscillate from one to the other. The Sudbury Neutrino Observatory experiment was designed to detect, for the first time, all three types of neutrinos. The other experiment just looked at the electron neutrino, mostly. You kind of looked at some of the others, but no, Snow was looking at all of them. And in 2001, Snow found that the total neutrino was exactly as John predicted 40 years before that. They found all the neutrinos from the sun, and it matched exactly what John predicted. And the only reason that Ray found a third of it only, the whole solar neutrino problem, was only because 2/3 of those neutrinos changed to different types of neutrinos. And Snow detected them, and Ray Davis' experiment could not detect them, and that was not expected. So when John heard that in 2001, and I'll show you a clip, he was just, of course, elated. He said, I feel like dancing. He was so happy because, you know, he worked on it for 40 years, and at the end, and so many people doubted him and Ray Davis for decades, and he was right. There you go. He was happy. He was a happy person anyway. So this was changing the physics books, and it's a nice story of science, how sometimes science is done. What started as a simple question, how does the sun shine, resulted not only in answering the question, we know now that the sun and other stars shine by nuclear reactions, but it revealed a whole new physics, neutrino oscillation, that requires mass for neutrinos. And the standard model of physics and the textbooks, they need revising now, have been revised. It's still not clear what is a mechanism that needs to change in the standard model of physics because of this result. And all of it started with Bahcall and Davis and many scientists in the bottom of the mine here. And again, I want to emphasize that the discovery of this big discovery of the oscillation and the mass and the discrepancy cannot be done just by observing something in a mine if you don't have something to compare with. So Bahcall's solar model was critical to get the discovery. If you just find some neutrinos, you don't know what to do with that. You mean, what is expected? Do I find more, less, the same? You have no idea. That's why the two of them were really working together all along for all these decades to solve that mystery. So, and here John gave a talk called Amazing at some point when he received some, I think the David Award, Amazing. And I want to read it because that's how he felt, and that's how I felt when I walked down today in the mine, and I think I told some of you when I walked down and visited all the caverns and so on. I find it amazing, almost incredible, that the century-and-a-half long chain of reasoning about how the sun shines and how neutrinos get to us from the sun could be tested on the basis of an experiment in the bottom of a mine. So you think about it, you're at the bottom of a mine and you're trying to figure out what happens at the center of the sun. I mean, it is really pretty mind-boggling. I kept thinking about it the whole time that I walked down there today. I'm amazed that so many people speaking so many different languages and living at such different times have collaborated in so many different ways to make it possible that flashes of light in the bottom of a mine could be used to determine the temperature in the interior of the sun and the properties of exotic subatomic particles. I'm amazed that flashes of light in a mine, the temperature of the sun, and the properties of neutrinos are linked in such a beautiful way. So, you know, he was just so delighted with that. I'm going to skip. Yeah, let me say that. Here is what I said, and it's good to know for science and for the history. I always tell students, look back at the history of how science developed and done, and how people sometimes criticize, and then what you do to overcome it. It's important to know in order to know how to deal in the future, or when your work is criticized at any given time. It's not to be stubborn, but to be very careful about it. Here is Bruno Pontecorvo, a very famous Russian physicist. Unfortunately, the weight of the thermonuclear reaction in the sun and the central temperature of the sun are insufficiently well known in order to allow a useful comparison of expected and observed solar neutrinos. He said it for a long time, for 3 decades. Howard Georgi and Michael Look, 2 very famous physicists. Most likely, the solar neutrino problem has nothing to do with particle physics. It is a great triumph that astrophysicists, like John, are able to predict the number of boronate neutrinos to within a factor of 2 or 3. And he got it to within maybe, I don't know, 10, 20%. That's what top physicists said. And C.N. Yang, a Nobel-Prize-winner, I did not believe in neutrino oscillation even after Davis' painstaking work and Bahcall's careful analysis. The oscillation were, I believe, uncalled for. So you see, it's not what people think just in theory. You have to measure, you have to test it, and then you may discover something totally unexpected. And that's how big discoveries happen. That's how dark matter discovery happened. Nobody expected it. That's what I work on. That's how dark energy was discovered. Nobody expected it. That's how solar neutrino masses were discovered. Nobody expected it. So it's important to remember that. Let me skip that so let me show you a little video of what John said, so you can hear John in his own words, when the snow results came. So he was really very, of course, very, very happy with that. Let me say a few more things about, because they asked me to talk a little bit more about John's work. But before I get that, I say, as you all know, the Nobel Prize in 2022 was awarded to Davis and Koshiba, the person who conducted the Japanese experiment for the detection of solar neutrino. John was expected by everyone to share in that prize. He didn't. I think the Nobel Committee clearly made a mistake on that one, as everybody told me that. And as the famous Nobel physicist Steve Weinberg frequently said to many, he said that without Bahcall theoretical work, there will be no discovery because there will be no comparison, there will be no solar neutrino oscillation, there will be no solar neutrino mass. You won't know what to do with the few neutrinos detected. It will not mean all that much. So that was in 2022. In 2015, but John was elated that the prize was given for solar neutrino. He felt that was a great recognition of the science, of the achievement, of the discovery, and he was very, very happy with that. In 2015, the second Nobel Prize was awarded to McDonald and Kajita. McDonald is a close colleague of John and myself, who ran the SNOW experiment. And here Jared worked with the SNOW experiment for neutrino oscillation. Again, we were told actually by the Nobel Committee, Bahcall was expected to share that prize for oscillation, but it was too late. So, but John was a pioneer and a leader in many fields. So while he worked on solar neutrino for 40 years, he did so many other leadership, pioneering work in astrophysics that many people told me they thought John Bahcall was, in solar neutrino, was different than the John Bahcall of astrophysics, because how could he do all of those things? But he did. So he worked and led, pioneered and led dark matter, distribution of dark matter in our galaxy. He did one of the best works on the structure of our galaxy. It's still called the Bahcall-Suniera model, and people are using it. How is our galaxy structure? He one of the first who did properties of quasars. He worked on black holes. It's still, many people are using the Bahcall-Wolf model about how stars are distributed around black holes, and it's being used every day now on black holes. worked on X-ray binary system, globular clusters, and many more fields, and he led many of those fields. He was also a seminal leader, important leader in the astronomical community. He was president of the American Astronomical Society. He was president-elect of American Physical Society. He led the Bahcall Decadal Survey in astronomy, proposing the main missions and experiments to do for the 1990s in astronomy. He's been advisor to Congress for many, many years. They always like to get his advice to NASA and the government. He was chair of astronomy at the National Academy of Science and many, many others. He was also famously a leader and advocate of the Hubble Space Telescope for several decades from the beginning, way before Hubble was launched. And he saved the Hubble from cancellation through Congress. He really was a very good policy advocate with Congress. They loved talking to him, and he was very persuasive with them. And he stopped Congress from canceling Hubble several times. As a reward, I can tell you a nice story. The astronaut who went, John Bahcall, who went the last time to Hubble for the final repair mission, maybe a dozen years ago, wanted to take something personal of John to the Hubble. I gave him our wedding rings, John and my wedding rings. He took it with him to the Hubble, went up, did all the orbits around the Hubble and repair Hubble, and brought it back. So our wedding rings went to the Hubble and back. And also related to here, John was a strong advocate for SERF. At that time, it was just creating a national underground lab. He kept pressing to agencies and others how important it is to have a national underground lab to do all these experiments that you are doing today, neutrinos, dark matter, and others. And he was, like he succeeded in Hubble, I'm sure he would have succeeded in helping you get more of what you need now. If you need, I'm happy to help, because it is very important. He also was a great advocate and participated with ice cubes. They have Bahcall fellowships there. NASA has the auditorium, main auditorium named after John, and many others. And he received numerous awards, the National Medal of Science from President Clinton, the Dan David Award, the first Beta, famous Hans Bethe Award, Franklin Medal together with Davis, and many other medals, including all the three top NASA Distinguished Award, and all the top American Astronomical Society awards, and many more. Here is John receiving the National Medal of Science from President Clinton for his fundamental contribution to areas of modern astrophysics, ranging from solar neutrino physics to the structure of the Milky Way galaxy to cosmology, and for his leadership of the astronomical community, especially his tireless advocacy of the Hubble Space Telescope. Again, that's how it started. That's John and Ray, how many, 60 years later? That's in front of the National Academy of Science building. This is myself and Anna Davis, Ray Davis' wife, when we visited the mine in 2008. We'll have some more pictures from today. This is John right here at the center with a blue shirt, working not in his office, but in the library near his office with his colleagues. Some of them are solar neutrino theorists. He always had some of them working closely with him. This is with President Clinton. That's, I promised you, me and John, I don't know, 40 years? Yeah, 40 years later. So those were 40 years amazing for neutrino for John, and those were 40 years amazing for John and for our life together. And this is John and myself and our 3 children, Safi and Dan and Orly. And I want to leave you with the last one. That's another video, a clip where John was interviewed for a program on PBS Big Ideas, where he was asked, why did it take, how does it feel that it took 40 years or 35 years or so? So you can hear him in his own.
30 years between the time you made your prediction and when you were vindicated.
37.
37. I'm not going to cheat you of 1 year.
Every one of those was a long year.
Well, tell us about that. What kept you going all that time?
I think it was just curiosity. It certainly wasn't didn't look like a good career move. I think historians of science, some of them, very often get the motivations of scientists wrong. I think very few of the people that I know who really are deeply involved in their science do what they do for professional reasons or make decisions about what they work on for reasons of that it's good for your career or good for anything else. You do it, I suppose, because you can't do anything else.
Just because you're curious.
You're curious, that's right. But I failed if I haven't told you that the main thing that kept me going and that kept Ray Davis going was it was fun. Because it's not often that you have a chance to combine microscopic physics, elementary particles on the smallest scales of the most peculiar kinds that interact the most weakly that we know of particles, with an attempt to understand the interior of the nearest star that's going to give you information about other galaxies and about the evolution of the universe. You know, that's a wonderful opportunity. And if you get banged around professionally or you have a long dearth of 2 or 3 decades when there are no new experimental results, what keeps you going is just, you know, the bizarreness of the activity that you're involved in, the uniqueness, the opportunity to do something that's different and fun.
But you know.
Okay, thank you very much.
Thank you. Thank you so much, Neta. If we have any questions, I'll come around with the mic and let you voice them into the mic. So we'll take a few minutes for questions. You answered everyone's questions.
Everybody is absorbing it, huh? Takes a little time to absorb it. Feel free to ask anything you want about the science, about John, about Ray Davis, about the experiment, about anything else.
About you.
Yes.
Yeah.
Tell us about your studies.
My studies.
Your work.
Okay, so I can actually I have a few slides, but maybe it's easier. I don't know if you want me to show. I can just talk. If you want, I will show us a few slides. I did prepare because they asked me to also talk about me. I decided to talk about John. I thought that was more important and interesting in connection with the lab here. I work in astronomy, and I work in understanding the evolution of our whole universe. I work on understanding the properties of galaxies, how galaxies form, how all the structure that we see in the universe formed and is evolving. One of the work that we did that relates to some of what we talked about is measuring. Our group was one of the first to determine how much dark matter exists in the universe, the total amount of dark matter in the universe. We know today that most of the mass in the universe, most of the gravity, is not the stars or the galaxies or the normal atomic matter that we see, but it's something new. You have much more gravity, and that's called dark matter. That's the majority of the mass in the universe. And it was not known. It was not known early on if it was zero and almost no dark mass, or it was a lot where the total energy density of the universe has what's called the critical density that stops the universe from expanding. If you have enough gravity, the expansion of the universe stops, halts. That's called the critical density. We found, using different methods of analysis, is that the mass density of the universe is much less than critical, only about 25% of the critical density. That means the universe will expand forever. Not enough gravity there to stop the expansion and make the universe recollapse. So we determined it in different methods. Some years ago, by now it has been verified by other measurements that is indeed the major standard model of cosmology today, that the universe mass density is about 25%, and then you have something else called dark energy, which accelerates the expansion of the universe, which we are also working on. Now we are also looking to see, I work on, with my students, on how is a dark matter distributed on large scale, because you cannot see dark matter, right? Dark matter means it's dark. You cannot see it with your telescopes. You can see the stars, you can see the galaxies. You cannot see the dark matter, so you can ask, well, how do you know it's there, right? How do we know it's there? Because if you have any gravity, it influences what goes around it. You know, gravity influences us as we stand on our planet Earth. If you have dark matter in galaxies, the stars on the outskirts will move faster than if you didn't have matter there. So we measure these velocities, and we see that they move faster than expected. So again, either general relativity is wrong, Newton is wrong, which is unlikely. If that is not wrong, you have to have dark matter. That's how we know. So we see it from the gravitational effect. There's also gravitational lensing today that Einstein predicted, that we can see how much matter exists because we see gravitational lensing. And if you want, I can show a few slides of that. But you can ask me, then I can show the slides. I don't want to take too much of your time. But that's what we are working on. And what we are finding is that dark matter on the large scale is mostly following all the galaxies that we see. So it's not distributed in a different way. It's not there where there is nothing, but it follows the distribution of galaxies on the large scale. So that's what topics I've been working on recently.
See, that's why I asked. I knew there was something behind this, where John was working on the sun, and your first statement was, well, I work on the rest of it. I just had that idea. Thank you very much.
Not quite that. As I showed you, John worked on the rest of it too, although the papers that you mentioned, we worked together. A few were on the solar neutrinos in the very early days when I was a student, and then we did a few other papers on some of the other topics. But he really worked on very, very broad things. Yes?
My question is, I work with students, I do education outreach. I'm curious as to what maybe sparked you when you were young to follow, to get to the path you're in. Like, what was it that inspired you or made you first curious?
That's a very good question. What inspired me, you know, unlike many of some of my students I talk to or read applications, you know, as a young kid, I looked at the sky and loved, you know. No, I didn't start that way. I liked science because from school, middle school, high school, because I had a wonderful science teacher. He taught chemistry, physics, and he was just so, he made it so exciting and so much fun, and I just loved that. And I decided to continue that because of that wonderful teacher. And you know, I enjoyed it more than writing long history papers, and that inspired me. And I thought, I studied physics and math, and I thought I took a teaching certificate because I thought I'll go back and teach in high school because he was so inspiring to me. But I finished, I graduated, and then I thought, I can wait with the teaching, I'll continue, get my second degree. And then I met John when I did my PhD at Weizmann Institute, and then I got married. You know, it's kind of, It went like this random walk. And then moved to Caltech, and then I just continued and studied astronomy. I studied physics. In Israel, there was no astronomy then. So I didn't know much about astronomy. I studied nuclear physics. I worked on an accelerator, on a small tandem accelerator that I saw the images today down in your basement. In the mine. Once we got in there, it felt like a basement. I just, at Caltech, where John was and I moved, I finished my PhD, and Caltech was and still is a powerhouse in astronomy. And I started talking to people there, and I was just amazed at the question that they were asking. It was at that time even, some of you may know the name, very famous astronomer Fritz Zwicky, who really the one who discovered dark matter in the 1930s. I started there in the 60s. He was there already, very old, but he came and talked to me and told me about dark matter, and I was just amazed by that. And since then, I just fell in love with astronomy. I thought the questions of what is the universe made of, how is structure formed, how is the universe evolving, they were so fundamental and so exciting and so mind-boggling that we can sit here on planet Earth and answer this question. I mean, if you think about it, I tell it to my students all the time. If you stop from your daily life or daily work that you do in astronomy and think about the big picture, that we just sit here, we cannot touch the sun, we cannot touch the galaxies, we can only observe it and then figure it all out. Figure out the model of the whole sun. You cannot see it. That is pretty astounding. So that's what got me into it. And being a good teacher is so important because it can influence or vice versa young students. Yes?
I am not a scientist and I know nothing about anything.
No need to apologize for anything. Yeah.
So with all of these neutrinos leaving the sun, do they take something away from the sun?
Yes. They're not just the neutrinos. The neutrinos come out of the sun because they weigh they do have mass, and we know now because of that, but it's so little that it doesn't affect the mass of the sun. So the sun doesn't lose anything by mass-wise from the neutrinos that come out all the time. The sun also generates the light all the time. The energy comes from the nuclear reactions. And that's why it keeps shining, because the nuclear reactions still keep going on there. So it keeps generating. Otherwise, if we didn't have the nuclear reaction going on, the sun will shut off. It will become dark. And at the end of the evolution, that's what will happen to the sun. Once the fuel in the inside, all the nuclear reactions will be used, all the protons will become helium, then all the helium will become carbon, and all the, they do a few steps, it will shut down, and then the sun will become dead at the end. I mean, it will become black and dark. Actually, before that will be even worse, because before that, once the hydrogen reaction, the proton-proton reaction, finished, then the sun will start expanding, because it don't have fuel until the temperature in the inside gets much hotter, and then the helium starts burning, and the sun will become much bigger, and then it will engulf our planet Earth with its heat, and our planet Earth will die. But we don't have to worry yet. It's going to be probably another about 4 or 5 billion years. So. But that will be, yes. Yes, yeah. Yeah, so that's something to worry about a few billion years from now. Right now we have to worry about other things, yeah. But that's a good question, what comes out, yeah. It does not lose mass that way. And there are a lot of activities on the sun. There are solar winds and magnetic fields, and that also move energy in and out. Yes?
Did you have a chance to meet Vera Rubin for that, that famous?
Say it again?
Vera Rubin?
Yes.
Did you have a chance to meet with her?
She was one of my best friends. Oh, she was a very good colleague and friend for many, many years, decades, for me and of John. And yes, we got together very frequently. When I go to Washington, I would go visit with her. When she comes to Princeton, she would come visit with me. And so we were really close friends. We didn't collaborate, but talked a lot about dark matter and the observations. She did the flat rotation curves. In fact, when she passed away a few years ago, I was asked and wrote several obituaries or retrospectives for her for Nature and for Science and for PNAS and others. So she was a very dear colleague and friend of mine. She was a remarkable person. Yeah. Yes?
Did John or you have a lot of influence on the upcoming deep underground neutrino experiment?
On which?
The deep underground neutrino experiment going into the Sanford Underground?
Yeah, John did. He did work pretty hard. Again, I don't know the detail. Maybe Jared knows. I don't know the detail, but he worked with, I don't remember who are the people who are pushing on the initial stages of getting the deep underground, Dussel it was called. So he really worked hard with Congress to try to get it. He worked very hard with your, I think, senator at the time. I remember that, Deschel, right? It was Deschel? So he met with Deschel several times in Washington and some other places, I don't know, maybe even here, and really got him involved and helped push it. John was very good in all this policy and advocacy and was very successful in that. He was very persuasive. And so he worked really very closely with Deschel and tried to get the Dussel lab. And he kept saying what I just mentioned, that how important it is, how unthinkable it is for a country like the United States not to have a national underground lab to do this very important experiment. Europe is doing it all the time. United States cannot not have that, just send scientists to do it there. So he really pushed hard to get it done. Any other questions? Yes?
Do we have an estimate on how fast those neutrino oscillations actually take place? Because we're not very far from the sun.
That's correct. And there are many parameters that you'll have to ask the solar neutrino people who will know better than I do. There are different parameters of the solar neutrino mixing and of course the mass that comes out of it, or the mass difference. And that is work that is still being done. What is the mixing strength and how they oscillate? And some of the planned big neutrino experiments for your place here, for SELF, is the upcoming Dune experiment that will help determine it. And that is a very important question, and they will help determine it. Is that correct? Do you want to add any?
Yeah, no, it's definitely a very important part of the strategic planning for science in the U.S. and for pinning down the ultimate cause of why there's more matter in the universe than antimatter. So doing precision measurement on the oscillations that the neutrinos experience, neutrinos and antineutrinos will tell us something about the matter and antimatter balance. And so it's an extremely important science endeavor that
So how fast they oscillate, it depends on the energy. Each of these neutrinos that comes from the different reaction have different energies, so don't calculate it. So it depends on the energy of the neutrinos, the scale that the Dune or any experiment will test it. So that is important work to be done to answer the question that you're asking. What Jared said is, which I did not mention, is the fact that neutrinos have mass and oscillate may be an important clue to understand even the bigger mystery of why do we have mass, why do we have just baryons in the universe? Because the expectation is from physics, and physics is not always exactly right, as we just saw. Expectation is that in the very early universe, the universe created just from, the universe didn't start with baryons, it started just from very hot energy. Universe, from the energy, universe created baryons and antibaryons in the same amount, and then they would cancel each other and we'll have nothing. So we have some asymmetry here. The fact that we have matter today, baryons today, how come? Nobody knows. And it's possible that the neutrinos, the fact that they have mass, once one figures out why they have mass, once you know how to change the standard model of physics, they may give you a clue of why we have this asymmetry between baryons and antibaryons, and therefore something annihilated baryons and antibaryons, but there was a tiny little amount of baryons left over antibaryons, and that amount is what we are made of today.
I didn't realize neutrino mass and matter-antimatter asymmetry were related at all.
That you'll have to ask in more detail the physicists who work on that. But yes, the answer is that there may be a clue to the production of matter. Did I explain it correctly?
Awesome.
One can probably get more information online, some papers, to really see the exact connection of what the process is to anything. But that's another huge question of why do we have baryons today, and why do we have anything today baryonic? Everything should have been cancelled if there was perfect symmetry. But clearly there was some asymmetry, and that asymmetry created all the baryons. We, the stars, the galaxies, all the baryons that we see today. That's not the dark matter, because dark matter, we don't know what it is yet. So we don't know much what to say about it. Yes?
What's your favorite role of the dark matter?
God, you know, I was asked that so many times the last 2 days. You know, I said before, it's $1 million question, it's $1 billion question, because we really don't know. The particle theorists have been suggesting WIMPs, the weakly interacting massive particles, as the most likely dark matter particle to fit their theory for many years now. Many experiments have been done, and that is just so puzzling that for decades we've been doing experiments to detect dark matter, to detect WIMPs, and some others, but mostly WIMPs. And the detection threshold go down and down and down and down, and nothing is detected. Your experiment here, the LZ experiment, is going farther down than anybody, and we all keep our finger crossed that you find something there. But when I talk to the particle physicists, to my colleagues, they are getting a little, some of them, not all, are getting a little concerned that nothing has been found, and the threshold are getting, some of them below what some of their theories would have predicted. And they exclude already some of the physics model. Also in the Large Hadron Collider, they don't see any signature or tail of signature of WIMPs. It could be that it's much higher energy, but they would have expected to see some. So they don't see it. So some of them are getting a little suspicious whether it is WIMPs or not. So there are many more attempts now to look at lower mass, to look at axion, to look at fuzzy dark matter, to look at other things. And the worry that I have is that if the WIMPs are not found in some of these best experiments that are being done now, we are open, we are going to be left with a very big, open, big question of not even knowing where to look next, because you don't know which mass range to look at, which energy range. And for each mass range, you need different detectors, so you cannot build all of them. So it's a very puzzling thing. So I do hope very much that it's a WIMPs and we can detect it, and hope that the LHC can see some signatures, some tails of that. But I think the answer is really not known at this point. And the fact that it already conflicts with physics, as I showed you the example of the solar neutrino, the physicists are not always, their theory is not always right. This one, the solar neutrino one, the neutrino physics needed changing. The dark matter may need changing, their expectation for WIMPs.
All right, well, we are at time for tonight. If you have any other questions, I'm sure Neta would love for you to come up and shake her hand and ask her. So let's give her one more round of applause.